The goal of the Ball-on Beam project was to design a beam that could balance a 100-gram steel ball on a straight, smooth track. The track could either pivot at the center and be between 12 and 24 inches long, or pivot at one end and be between 6 and 12 inches long. The beam was controlled by an Arduino microcontroller. A sensor was needed to track the position of the ball on the beam, and an actuator was needed to control the motion of the beam. To be successful, the ball had to be placed 4 inches from the pivot point and then remain within 5 inches of the pivot point for at least 20 seconds. Our beam was 12 inches long and pivoted at the center.
The beam apparatus was manufactured using the machine shop provided by Rowan University. The stand was cut out using the water jet. The pieces were then drilled and tapped on the mills to allow for easy assembly and disassembly. Next, the beam was cut out using the laser cutter. The beam's end caps were also drilled and tapped on the mills to allow for easy assembly and disassembly. The end caps prevent the ball from rolling off either end of the beam. The beam was assembled, incorporating a V-shaped track to prevent the ball from rolling off the side of the beam. One side of the track was extended to accommodate the length of our sensor, a linear potentiometer. The servo motor, our actuator of choice, was bolted to the stand and the beam to the servo. The potentiometer and servo were then wired to the Arduino microcontroller and ready to be programmed.
An equation was determined to model the forces acting on the beam. These forces consist of the moment of inertia of the beam, multiplied by the angular acceleration, the damping coefficient of the system multiplied by the angular velocity, the spring constant of the system multiplied by the angle, the torque output of the servo, and the moment due to the weight of the ball. The moment due to the weight of the ball was calculated by multiplying the mass of the ball by gravity times the distance from the center of the beam. However, since the stiffness of the system is much lower than Kp, the PID control is independent of this equation.
The system uses a linear potentiometer to sense the position of the ball. A linear potentiometer uses variable resistance based on the location of contact along its length. It outputs an analog signal between the values of 0 to 1023. The output of the linear potentiometer must be mapped into the range of the servo input, which is 0 to 179. This is the position range of the servo. Then the output to the servo was experimentally compared to the actual angle. The position range does not directly correlate to the angular position of the servo. The set point is the servo output that sets the beam to the horizontal position. The reaction of the servo was limited to 10 degrees in both the clockwise and counterclockwise directions by remapping the servo output. The position reading from the potentiometer minus the set point in the center of the beam equals the error used in the PID equation. The PID equation is used to calculate the corrective control action. The integral and derivative of the error is calculated for use in the PID equation. The error, integral, and derivative are scaled by the Kp, Ki, and Kd constants respectively. The sum of these scaled factors equals the corrective control action. The output to the servo is calculated by subtracting the corrective control action from the set point. In order to achieve the desired behavior of the beam, the Kp, Ki, and Kd constants are tuned experimentally. The Kp constant affects the magnitude of the reaction by scaling the error. The Ki constant reduces small amounts of long-term error. However, this was not necessary for our system. The Kd constant damps the oscillation due to the Kp, making the system more stable. The optimal values for Kp, Ki, and Kd were 0.5, 0, and 0.2 respectively.
During tuning, the Kp value was originally set to 1, while the Kd and Ki values were left at 0. This Kp value proved to be too high and caused the ball to oscillate back and forth along the length of the beam. To correct this problem, two things were done. First, the Kp value was cut in half and set at 0.5. Second, the Kd value was increased to damp the oscillation. The original Kd value was too low and did not damp the oscillation quickly enough. To correct this problem, the Kd value was increased from the original value of 0.125 to the final value of 0.2. This proved to be high enough to keep the ball within the range of -5 to 5 inches.